you, Dr. Neetu. So, participants, we have come to the second session of the day, and this is a talk being given by Dr. Sourav Sur from Department of Physics and Astrophysics. He has already given many lectures before this, so you are well acquainted with him. So, it is my pleasure to introduce Dr. Sourav formally. Dr. Sourav did his PhD in 2005 on the thesis entitled Cosmic Phenomena in String-Inspired Space-Time Distortion from Jadavpur University, Kolkata, India. He had worked as a postdoctoral research associate at the Institute of Physics, Bhubaneswar, India, University of Lethbridge, Alberta, Canada, Saha Institute of Nuclear Physics, Kolkata, India, before joining as a regular faculty member at the Delhi University. He has taught many core and special theory and lab courses in the curriculum of master's degree program at the Department of Physics and Astrophysics, University of Delhi. His main research area include classical and quantum gravity, cosmology, quantum entanglement and black holes, astrophysical and cosmological aspects of string. He has more than 25 research papers and has guided many PhD students so far. His name is included in the reviewer panel of several research journals of international repute and has received recently the Outstanding Reviewer Award 2019 from the Journal of Classical and Quantum Gravity, Institute of Physics, Publishing, Bristol, UK. So, Dr. Sourav, I welcome you again to the webinar series, and I request you to kindly, share your screen and start your presentation.
Okay, sure.
So, Neetu, you can stop sharing. Yeah.
Yes, thank you, ma'am. We welcome you, sir.
Yeah, my pleasure. All right. Can you see my screen?
Yes, we can see your screen. We can't see the PPT.
Okay.
We can see the Zoom.
Okay. Yeah.
You're sharing it now. Yeah, we can.
So I'll start from where I left yesterday.
Definitely.
So we are dealing with the covariant formulation of electrodynamics. Basically, we started off with the formal definitions of the charge density and the current density in terms of point charges and the flow of point charges given by the velocities of the respective charges in a system of charges. The point charges are designated by the delta function. And then what I have defined is something similar to, analogous to the three-dimensional current density. This is the four-dimensional current density, which actually encodes the three-dimensional current density as the time component and the charge density as the time component and the three-dimensional current density as the space part. So then the equation of continuity reduces to just a divergence equation, similar to what we have in magnetostatics. We have the divergence of the current is zero. So that's what we get here. And this encodes the conservation of charge and current, the full configuration. So what we call the four current conservation. So this I did yesterday. And then going to the covariant generalization of the Lorentz force equation. This is the Lorentz force equation, the three-dimensional Lorentz force equation. Q is some point charge. And in an electromagnetic field, we have the force exerted on the charge when the charge is subjected to those fields, to the electromagnetic field. I should not say those fields, because from now on, electric field and magnetic field, they are not separable, as I'll show in a while. What we should say, the electromagnetic field in total. Electric field and magnetic field, they are only components of what is known as the electromagnetic field. And in fact, the electric field vector E and the magnetic field vector B, they don't have any unique significance. Only when they're talked together, or one has to make allusions of the electric field and the magnetic field vector together, or what is known as the electromagnetic field tensor. So this Lorentz force equation is generalized to this form. This is the electromagnetic field tensor. This transforms as a contravariant tensor of rank 2, antisymmetric in the indices alpha and beta, and u beta is the 4 velocity or the world velocity. And this encodes the components of the E vector and the V vector in this fashion. This I illustrated yesterday. And this is the proof that this tensor indeed, this object indeed transforms as a tensor of rank 2, a contravariant tensor of rank 2. Next comes the covariance of Maxwell's equations. So we have the Maxwell's equations, the two equations, two inhomogeneous equations, 1 and 2. One divergence equation and one curl equation. This is the three-dimensional divergence and the three-dimensional curl. And the right-hand sides are the sources, the source charge density and the source current density. Okay, and equations 3 and 4 are the homogeneous equations. The right-hand sides are 0. Here, the this dot denotes time derivative. In the index notation, these equations are expressed in this fashion. We use the Levitivator Tensor here. Since it's a three-dimensional relationship, we use the three-dimensional Levitivator Tensor, which is totally antisymmetric. The components are either +1 or -1, depending on whether I, j, and k are cyclic permutations of 1, 2, and 3, or anticyclic permutations of 1, 2, and 3. There are 3 indices, x1, x2, and x3. The first 2 equations that involve the sources can be encoded in this equation. This is the 4-dimensional equation. This is a tensor equation. The left-hand side is the divergence, the covariant divergence of the electromagnetic field tensor. And the right-hand side contains the forecurrent. The component equations are this. So this alpha is summed over. So you have the free index beta. Beta can take 0, that is time, or a space index. If you put beta equal to 0, then you get this equation. Then you get this first equation. And when beta is a space index, then you get this equation. And this I also have illustrated. This equation is nothing but this equation. When you put the components of the electromagnetic field tensor in here, F0k is minus EK, and Fik is epsilon IKL dl. So if you put this in here, you get this equation. Whereas if you put the value of Fi0 here, you get this equation. Although I'm saying this equation, note that this is one equation, and this contains 3 equations. because this is a vector equation. Okay, the vector has three components, so there are three equations here, one equation here, one equation here, and three equations here. Okay, so there are altogether 8 equations. Similarly, one can encode the other two equations in some other as a divergence of some other tensor, second rank antisymmetric tensor, which could be constructed out of the electric and magnetic field vector components. By inspection, you can check that if I construct some tensor f tilde alpha beta, which, like the electromagnetic field tensor, is also constructed out the components of E and B as this, then the components are given explicitly by in this form. Then the second equation that comes is del alpha of this thing. This tilde f tilde alpha beta is nothing but what is known as the dual of f alpha beta. This is sometimes called the Hodge dual. This star is the Hodge star, and this is the dual of f alpha beta. Let me go back to the tensor duality we had yesterday. I'll not spend much time on this because I have already given you a worksheet, and we're going to solve some problems on the worksheet, possibly all the problems in the worksheet tonight. So let's spend some time, as I have shown yesterday, that this equation encodes the two Maxwell's equations, the inhomogeneous Maxwell's equations. This equation with star f alpha beta or f tilde alpha beta given by this would encode the last two equations. Okay. Going back to tensor duality, let's get back to the tensor duality. See, maybe I should open it different. Wait a minute. I'll of course post all these annotations. So we skipped the tensor duality yesterday. So let's do it. All right. So I talked about the symmetrization and antisymmetrization of tensors, symmetric and antisymmetric tensors, and so on. And I introduced the metric tensor, which is a symmetric second rank tensor. And it doesn't matter what is the dimensionality of space-time, 3-dimension, 4-dimension, 5-dimension, whatever you take. This metric tensor is always a second rank tensor. There is another fundamental tensor, which is the Levitivator tensor. Okay. By the way, we are using the Minkowski metric only because we are concerned with special relativity here. There is another fundamental tensor known as the Levitivator tensor, which I can introduce. So a completely antisymmetric tensor of say rank D in D dimensions, completely antisymmetric tensor of rank D is proportional to this tensor, which has values -1, for alpha 1, alpha 2, the indices be an even permutation of 0, 1, 2, and so on. Plus 1 if alpha 1, alpha 2 are odd permutations. Even permutation means cyclic permutation. Odd permutation means anticyclic permutations. And similarly, the contravariant piece can be written in terms of the contravariant Levitivator tensor, whose values are plus 1 for the indices to make an even permutation of 0, 1, 2, and so on, and minus 1 for odd permutation of 0, 1, 2, and so on, and 0 otherwise. 0 otherwise means no two indices could be same. Okay, so you cannot have, things like this, epsilon 1, 1, 2, 3 is identically 0. No two indices could be same because it is antisymmetry. Because of the antisymmetry, no two indices could be same. And epsilon 0, 1, 2, 3 in 4 dimensions is plus 1, whereas epsilon 0, 1, 2, 3 is minus 1. So this is the thing. And under the interchange of any pair, it picks up a minus sign. So for example, epsilon 1, 0, 2, 3 is minus epsilon 0, 1, 2, 3, that is minus 1. Similarly, epsilon 1, 0, 3, 2 is the same as epsilon 0, 1, 2, 3 plus 1. Okay, so there you have a double interchange from 0, 1 to 1, 0, and from 2, 3 to 3, 2. So two interchanges. So when you have two interchanges, there will be two minus signs. So it would be ultimately plus sign. So for example, what would happen to epsilon 3, 0, 1, 2? The way to do it, first take interchange 3 and 2. Then you have 0, 1, 3, 2. It will pick up a minus sign. Then put the 3 in here. Then there will be double interchange. So plus 1. And then finally, 3 would be interchanged with 0. So triple interchange, that means it would be minus 1. The indices are raised or lowered as usual with the metric tensor. And in our case, the metric tensor is the Minkowski metric tensor. And there are these are the contraction relations between the Levitivator tensors. So contracting all the indices, you get 24 or minus 24. This is 4 factorial. When you contract 3 indices, you'll have 3 factorial and then a Kronecker delta of the free indices. Okay, these indices nu, lambda, and sigma, they are repeating, so summed over. The free indices are mu and alpha, so you have delta mu alpha. And similarly, when you contract 2 indices, you get this is known as the generalized Kronecker delta. This is defined in this way. And this is a further generalized Kronecker delta. So these are basically determinants of Kronecker deltas. Explain this in a short form. Okay. Say you have a tensor, let's say a third rank tensor, T alpha beta gamma, which is completely antisymmetric. Okay, it is completely antisymmetric. That means it will pick up a minus sign under the interchange of any pair of indices. For example, T alpha beta gamma is minus T beta alpha gamma, and this is equal to T alpha beta gamma is also minus T gamma beta alpha. So here we have interchanged the first and second indices. Here we have interchanged the first and third indices. You interchange any pair of indices, it will pick up a minus sign. If you interchange two pairs of indices, then it will be minus and minus plus. So that, for example, it is equal to plus T beta gamma alpha. So from alpha beta gamma to beta gamma alpha, you require to make two interchanges. Okay, so that means two minus signs, which will ultimately give you plus sign. In this way, this will go. Now consider a fourth rank tensor, which is totally antisymmetric. Okay, you don't need to look into all these things. In simple terms, consider a fourth rank tensor, completely antisymmetric in 4 dimensions. How many independent components it can have? In 4 dimensions, it can have the indices are 4, 0, 1, 2, 3. So alpha, beta, gamma, delta should be permutations of 0, 1, 2, 3. But all of them should be different because this is totally antisymmetric. Otherwise, it's 0. So you have to make a permutation for which all the things is 0. So for example, you have T0, 1, 2, 3. That is non-zero. But this is not equal to 0. However, T0, 1, 2, 1, that is 0. Because here two indices are same. So you cannot have two indices same. So the possibility that you are left with is that there is only one component, one independent component exists. Okay. Because any other component, for example, T0, 2, 3, 1, this is dependent on T0, 1, 2, 3. So you can just flip the, you interchange 3 and 1 and then 1 and 2. You get back this relationship, this component. So this is not independent. These two components are not independent. So these are permutations of 0, 1, 2, 3 in different forms. So effectively, you have just one component, which is independent. So that means that although this is a 4th rank tensor of rank 4, okay, it's a tensor of rank 4 in 4 dimensions. How many components it should have? It should have, this is a 4 to the power 4 components. But it effectively has only one component. Similarly, in 4 dimensions, if you take this, then what are the possible permutations? You have 4 indices in 4 dimensions, 0, 1, 2, 3. So what permutations you can make? T0, 1, 2. Then, so put alpha equal to 0. Then you have beta gamma, which should not be 0. So beta gamma could be 1, 2, 2, 3, or 3, 1. So 0, 2, 3, 0, 3, 1. And you can also have T1, 2, 3. And nothing else. You cannot have anything else. You can have T0, 1, 2, T1, 2, 0, which is also dependent on T0, 1, 2. T0, 2, 3, T3, 0, 2, T2, 0, 3, they are all dependent on T0, 2, 3. So this is one independent component, this is one independent component, this is one independent component, and this is one independent component. So in 4 dimensions, what we see, although we have a third rank antisymmetric tensor, it effectively has 4 independent components. That means it is dual to a 4 vector. Similarly, a 4th rank tensor is dual to a scalar, 1 component, T0, 1, 2. So this is called duality. You can always, you can just count the number of independent degrees of freedom of a given tensor with a given symmetry property, symmetry or antisymmetry property. And then from there, you can see what the ultimate stuff, how many components the ultimate stuff has. If it has only 4 independent components, this is actually dual to a 4 vector. So this is the thing. In 3 dimensions, for example, this ijk can take 3 values, 1, 2, 3. So a completely antisymmetric tensor is dual to a scalar. This scalar is denoted by this star known as the Hodge star, okay, known as the Hodge star or the Hodge dual. It's written like in this fashion. Similarly, a second rank tensor in 3-dimensional space is dual to a vector. A vector, a covariant vector, is dual to a contravariant second rank antisymmetric tensor. So here we are dealing with all antisymmetric tensors. Antisymmetric tensors have this sort of duality. They form a large class of tensor algebra, large subclass of tensor algebra, and are hugely important in many contexts in physics, especially in quantum field theory. Also in sort of the Dirac algebra, for example. Even the classical Dirac algebra that uses this duality relationship. In 4 dimensions, as I said, a completely antisymmetric 4th rank tensor is dual to a 4-dimensional scalar. I'm saying it's a scalar, it's actually a pseudoscalar. So if this is a tensor of rank 4, this is a pseudo tensor of rank 0, that is a pseudoscalar. This epsilon is actually the measure of parity. In fact, in the Dirac algebra, there are some of you may know of heard about the Dirac matrices. Okay, the Dirac matrices. There are 4 Dirac matrices: gamma 0, gamma 1, gamma 2, gamma 3. There is a 5th Dirac matrix, which is known as gamma 5. And these are all 4 by 4 matrices. And this gamma 5 is actually defined as I gamma naught, gamma 1, gamma 2, gamma 3. And this can be correlated with the epsilon. This gamma 5 gives a measure of parity violation in, for example, the weak interactions, beta decay, for example. In weak interactions, we have heard about the violation of the parity symmetry, and the violation, say in the lepton decay, the violation is being designated by this gamma 5, or equivalently by this Levitivator tensor. So this is a measure of parity. So if the left-hand side is parity even, the right-hand side is parity odd. So not only you have a fourth rank tensor effectively culminates to a zero rank tensor, you also have a violation of parity on the right hand side. I mean, sorry, I should not say that. This stuff, star A, has opposite parity properties than this thing on the right hand side, on the left hand side. So these are called tensor duals. Similarly, when you have a second rank tensor like our F alpha beta, okay, F alpha beta, which is a second rank tensor in 4 dimensions, you can write this as half, just as I have written it. As I have written it, F right here. I think it should be 1 over factorial 2. No, it's okay. It's okay. So this is 2 epsilon alpha beta mu f mu star f mu. What does this mean? That means that given electromagnetic tensor, you can define another tensor, second rank, antisymmetric, but pseudo, that is of opposite parity property, constructed out of E and B vectors. Just as F alpha beta is constructed out of the components of E and B vectors, star F alpha beta can also be constructed out of the E and B vectors. The definition is this. So the inverse relationship, which is this or this. So you have star F alpha beta defined by half epsilon alpha beta mu. And this this star F alpha beta is actually what I have defined here, F tilde alpha beta. This is nothing but the dual of F. So that means that you have these 2 equations ultimately. These 2 equations. You had 4 Maxwell's equations. 2 of these non-covariant equations are encoded in this covariant equation, and 2 others are encoded in this equation. You can see one interesting thing, that forget about the sources. If the sources are 0, then these 2 equations look similar. These 2 equations look similar. The right hand side is a 0 for j equal to 0. And the transformation is this. F to star F means E to B and B to minus C. That is, wherever look at the forms. Here you change E1 to B1. So it is minus B1, minus B2, minus B3. Okay. And here you change B to minus E, that is plus E3, plus E1, plus E2. You land up to this. So this is what is called duality, and they can be written in this way. The next thing that comes is the transformation of electromagnetic fields. I'll note the derivation here because it requires the general Lorentz boost transformation. For a general Lorentz boost transformation, this derivation I will not do. For a single Lorentz boost along, say, the x-axis. So what we had previously, we have one frame. This is the x direction. This is one frame sigma, and there is another frame. The axes of the two frames are parallelly oriented. The origins coincide at the origin of time, and you have a single Lorentz boost. For the single Lorentz boost, these are the transformations. In the primed frame, the electric field, which would be recorded, has components in general differing from those in the unprimed frame. This is a very crucial thing and very interesting thing. You see, under just a frame transformation, you have transformed electric field which is not equal to the original electric field. One component is equal, but not the other components. Similarly, you have a transformed magnetic field which is not equal to the original magnetic field, that is the magnetic field in this frame. Okay. The other frame is moving with respect to this frame with velocity v along x prime. So in the other frame, you have this transformed magnetic field. So that means what? That means if you choose the velocity in such a way, so you move your system, your recording system or the detector from the source or the emitter in such a way, with such a velocity, you have to do a velocity selection. You have to put a velocity selector as a collimator in the experimental apparatus. Then, if you have both electric and magnetic field in one frame, you can have only electric field or only magnetic field in the other frame. That is possible under this transformation. This is really very interesting because by a suitable choice of this beta, you can actually put by prime, bz prime equal to 0. There are specific situations where you can put the full magnetic field equal to 0. Magnetic field in one frame equal to 0. Although there is magnetic field in the other frame. Similarly, you can put by choosing the velocity beta, you can transform to a frame, Lorentz transform to a frame in which there is only electric field or only magnetic field. Unfortunately, I have given a fourth problem on this transformation of electromagnetic field, but I don't think I'll have time to go through all those things tonight. I can do the first three problems, of course, but not the fourth one. I can give you the solutions though. Now, here is something quite interesting. First, see the norm of the electromagnetic field tensor. The norm, electromagnetic field tensor, the general form is given here. Here, this is the electromagnetic field tensor. So you can work out its norm from this relationship, from this structure. So let's do it. F alpha beta, F alpha beta. First, you take the sum over beta or alpha. So alpha could be 0, alpha could be a space index. So F0 beta, F0 beta plus Fi beta, Fi beta. Then beta could be 0, beta could be a space index. But here, if you put beta equal to 0, then if you have F00, which is 0. So it should be F0k, F0k plus, here beta could be 0 or a space index. I0, Fi0 plus Fik, Fik. Now you have F0k equal to minus Ek and Fik equal to epsilon IKL DL. So putting all this, you see, this is minus Ek minus Ek. So minus E square. Minus Ek means plus Ek. From this, you have because this is minus Ek times minus Ek. Minus minus becomes plus. You have this. Similarly, you have Ei, Ei. And then here, plus epsilon Ikj Ej, epsilon IKL DL. Here you see two indices are contracting, and I have just shown you here that these relationships two indices contracting. So in the when two indices contract, you have a factor of factorial 2 coming. Here, for example, this is of course in the 4 dimensions. You can do identical things in 3 dimensions. In 3 dimensions, 2 indices contracting, it will give you a -2. And EK or EI is minus E squared. So you have a minus E squared here, you have minus E squared here. So it will give you minus 2E squared. And here you have epsilon contracting, giving you a -2 and then a Kronecker delta. So you have a -2. What are the free indices? L and J. BJ, BL. Okay. So when you do this, you'll have BL, BL, upstairs, downstairs. So that will give you another minus. As I said, EK is minus E squared, not plus E squared. Similarly, BL, BL is minus B squared. So that minus and the minus here will make it plus. So it will be minus 2E squared plus 2B squared. And that's what is written here. Similarly, F star F will fetch you minus 4 E dot B. You know what is star F? Star F is star F alpha beta is half epsilon alpha beta mu F. So star F alpha beta F alpha beta is nothing but half epsilon alpha beta mu F mu F alpha. And doing proceeding in this way, you can work out the value. It's a scalar product, remember, it's a scalar product. All the indices are summed over, so it will be a scalar. In this case, there is a true tensor and a pseudo tensor, so it would be a pseudo scalar. This is a pseudo scalar. Okay, because it's the dot product of E and B is not a vector. B is a pseudo vector. B square is a vector, but B is a pseudo vector. B you can write as curl of A. So it can be written as a cross. So a cross comes in between. That means B is a pseudo vector. And E dot B, so a vector dotted with a pseudo vector is a pseudo scalar. But this is a true scalar because B square is a true scalar and E square is a true scalar. So this is a scalar, this is a pseudo scalar. Now, the consequences of this scalar invariance are as follows. If E and B, E is equal to B, that is the magnitudes of the electric field vector and the magnetic field vector are same in one Lorentz frame, then E prime and B prime, that is the magnitudes of the transformed electric and magnetic field vectors in another Lorentz frame should also be equal. If E is perpendicular to B in one Lorentz frame, then E prime is perpendicular to B prime in every other Lorentz frame, unless E prime or B prime vanishes identically. That is also possible, as I told you, because of the transformations. If E is parallel to B in one Lorentz frame, then the condition for E prime to be parallel to B prime in another Lorentz frame is that EB is E prime B prime. This follows from the fact that if theta is the angle between E and B in one frame, then the corresponding angle, theta prime, between E prime and B prime is given by this. So cos theta is EB divided by E prime B prime cos theta. So it's simple. You have E dot B equal to E prime dot B prime. So this means EB cos theta equal to E prime B prime cos theta prime. Okay. So and hence this relationship. Cos theta prime is EB divided by E prime B prime cos theta, provided E prime or B prime doesn't vanish. Therefore, when theta is 0, the condition for theta prime equal to 0 is EB equal to E prime B prime. This would be clarified as we go on, as we work out problems. Okay. Problems on this electromagnetic scalar invariants, scalar or pseudoscalar invariants. There are only two types. One is the norm of F, which is nothing but the norm of the star F, the Hodge dual of F, modulo this minus sign. And the other one is the scalar product of F and star F. Before we go on to the problems, let me mention one thing. Although there is one chapter which the next chapter, I'll urge you, if you those who are really interested in these things, please go through the next chapter. This is the covariant formulation. The next chapter is the potential formulation. Is the potential formulation of electrodynamics. You can see that this second equation, second Maxwell's equation, could be solved. This can be written in this fashion. You can check for yourself using the property of the Levitivator tensor that enters here. And this has a unique solution in this way, where A mu is some vector, and this vector encodes the scalar potential and the vector potential, what we had in the non-covariant approach. So just as we have encoded the charge density and the current density in a 4 current, similarly, the scalar potential and vector potential, the 3-dimensional vector potential, as a 4 potential. It is verified right here. Okay. And in the component form, you can just check out that these two, if you do this, then it will indeed give you E equal to minus grad phi minus 1 over C del A del T, and B equal to curl A. This is the cross check. The interesting thing is that going back to this the covariant formulation, we had 4 Maxwell's equations to begin with, and then we have written down 2 covariant Maxwell's equations. 2 covariant Maxwell's equations, which are this. In fact, if somebody asks you how many Maxwell's equations are there, you'll say 4 equations, as usual. But there are actually 2 equations. And in the covariant form, there is actually 1 equation. The equations, the Maxwell's equations are this, the 1 and 2, those which contain the sources. The other 2 equations are not equations in true sense. These 2 equations, this is the non-existence of magnetic monopole, and this is the Faraday's law. These are not equations. These are actually identities. And so is this, which encode these two equations in the covariant form. This one is an identity, and this one is the actual Maxwell equation. So actual Maxwell's equations are two, and the two others, the homogeneous ones, are identities. Okay. Now, how do what is the difference between an equation and an identity? The equation and identity, you have to be very careful when you call something which has a left-hand side and a right-hand side, whether that expression, one expression is equal to some other expression. That doesn't necessarily mean that it shows some equation. No, it could be an identity. In the strict sense, identity is something which is always satisfied. An equation is something which could be derived. Faraday's law was never derived. It was an empirical result. It's an identity. How to recognize that? When, let's say, you work out the equation for a system. Now, the system, to work out the equation of motion of a system, let's say, how to work that out? You do a variational principle. You vary some Lagrangian with respect to the potential. And then, after putting the variation equal to 0, you get the equation of motion. The potential here is the 4 potential A mu, which I have told you just now. When you, and I'll not write down the electromagnetic Lagrangian. It's actually, the electromagnetic Lagrangian is this. This is the electromagnetic Lagrangian. It's F dot F. And if you vary this Lagrangian with this potential A mu, do a variational principle, then the Lagrange equation of motion that we'll get is precisely this equation. So this is the equation of motion. This is the Lagrange equation of motion. This is never an equation. This is an identity. By solving this identity, you express the field in terms of the potential. Okay. Solving the identity, you get F mu nu, you write F mu nu in terms of the potential. You see, it's written as a covariant curl of this potential A mu. So with this, we shall switch over to the worksheet. I hope all of you have the worksheet. Let me show you once again. This is the worksheet 2. This is the worksheet 2, and I'll solve this this one and this one, and I'll also do this thing tonight. This fourth one, which is on the transformation of electromagnetic field, may not be possible because it's a very longhand exercise. It may not be possible tonight, but I'll give you the solution. Okay. So I'll try and do as much as I can tonight and give you the solution. Just give me 1 minute break before we start this. Start solving this. I'll take 1 minute break. All right, I'm back. Sorry for this interruption. So let's do this thing. The first one is to determine the equation of the world line of a particle of charge q and mass m under the influence of a constant electromagnetic field. That is, all components of the field tensor is constant. And remember that electromagnetic fields, you have to talk about the electromagnetic field, not the electric field and the magnetic field. Because in one frame, both electric field and magnetic field can exist. In another frame, only electric field or only magnetic field can exist. So the definitions are or the recognitions are ambiguous. Okay. You have this kind of uniqueness problem. To avoid that, we have to use the covariant language and use what is known as the electromagnetic field in all. And also, as a byproduct, I will explain how to show that the norm of the 4 acceleration is negative. I gave you the exercise yesterday to show that the norm of the 4x acceleration, a mu, is negative. That is, a mu vector is space-like. I hope some of you have tried that. I will, while we work out the solution of this, I'll show that the norm of a mu negative comes as a byproduct. Okay. So let's do this. Let me add a page here. Okay. Thing. Okay. So particle under the influence of a constant electromagnetic field. World line means the line the particle traces out in the full 4-dimensional space-time. The trajectory here in the third problem, the trajectory means the path of the particle in the 3-dimensional space. But world line means the path of the particle in the entire 4-dimensional space-time. If you want to learn more about the world lines, you can look at the chapter 4, which I have skipped. on the Minkowski diagrams. Okay, so this is some problems with the tablet. So we have the Lorentz force, F alpha. And F alpha is Q over C, F alpha beta, Q beta. Okay, so this is the F alpha. And the first thing here, all components of F alpha beta are constants. So F alpha beta is a constant tensor. So dF alpha d tau is Q over C. F alpha beta are constants, so I can write it F alpha beta d U beta d tau, or Q over C F alpha beta. This is problem number 1 we're doing. And this is the acceleration A beta. Now, from here, it can be proved that this Lorentz force has a constant norm. That is, this A beta, the norm of the acceleration is a constant. How to prove that? Well, the norm is F alpha, F alpha. So you can write this as the square of this. So this is Q squared over C squared F alpha gamma U gamma F alpha beta U. You cannot use the same dummy index, so you have to use a different symbol. Now, to show that this thing is a constant, you have to derive with respect to the proper time. Now, this is nothing but F squared. So this is 2 F alpha d F alpha d tau. So this first F alpha is 2 Q over C F alpha gamma U gamma. And the second one is this Q over C F alpha beta A beta. So you get this thing F alpha gamma F alpha beta U gamma A beta. So can you see from here that this is actually 0? You cannot. And this is a line of caution. You cannot. Because you are nowhere to prove nothing. You cannot prove anything doing this way. So why you were considering this? What went wrong? I can tell you that this thing is a constant and its time derivative or proper time derivative is 0. But you cannot show this way. Why? Because you have jumped steps. What I have done here, I have jumped steps. So the first word of caution in solving these types of problems, in fact, solving any problem, is that it's a bottom line, don't jump steps. Never, never, ever jump steps. What step jumping is done? See, we should not write it like this or like this. From here, we have this thing. First, we write to keep f alpha as it is. F alpha. Now take this thing, write this thing first. This is here. Write this thing. This is Q over C F alpha beta A beta. Now, what is force? What is force? F alpha. Force is mass times acceleration. Put that here. So this is 2m Q over C F alpha beta A alpha A beta. I have put F alpha as this, not F alpha as this. F alpha is also this thing. Okay. So you have to do it step by step. Don't jump any step. Now, what you see here, this product is symmetric. That is, A alpha A beta is same as A beta A alpha. But F alpha beta is antisymmetric. So you have a scalar product of some symmetric second rank tensor A alpha A beta. This product you can think of as a second rank tensor, and an antisymmetric second rank tensor. The product is zero. Okay. I have illustrated these point by point. Okay. So keep this in mind. I don't have time to illustrate all the things point by point, which with each and every minute step. But you have to be careful where people do mistakes. So this is a common place where mistakes could be made. And once you make the mistake, you are nowhere to prove anything or to work out anything. So what does this mean? This means that F alpha is constant. So This means that the norm of the Lorentz force, the covariant Lorentz force, is constant. And F alpha is m square A alpha. So if F alpha is constant, this means that A alpha is also constant. So we have proved, we have worked out that a constant electromagnetic field means the constant for acceleration. But we require to find out the trajectory. To do that, first work out A alpha. That is the exercise I gave you yesterday, to work out the norm and show that it is negative. For simplicity, I'll give you, this is a trick. Don't do it in 1 plus 3 dimensions. Do it in 1 plus 1 dimensions for simplicity. Okay, so you have one time t and one space x, tx coordinate system. So then in 1 plus 1 dimension, you have A alpha as A0 square minus A1 square. A0 square minus A1 square. Okay. Now, what is A0? A0 is du0 d tau whole square minus A1 square is du1 d tau whole square. Remember, u0 is gamma c and u1 is gamma c1. So, and dd tau is gamma times ddt or dt over gamma. So, this is gamma square u0 dot square minus u1 dot square. So it's gamma square u0 dot is du0 dt. And u1 is gamma v1 whole dot square. Okay, if you work this out using the relationship that gamma is 1 over square root 1 minus v1 square by c square, then this will turn out to be negative. Okay, I'll give you the exercise to check that. This is the easier one. So you have to do it by reducing it to 1 plus 1 dimension rather than to 1 plus 3 dimensions. Okay. The rest of the problem I have already worked out, and I'll just go through those. because I have, I think, only half an hour left, and there are plenty of things to demonstrate. A little more than half an hour, maybe. So it's better to look into the worked out stuff. Let me do it. I'll save all these things and send. So this is the first part which I have shown you. So it gives you mu equal to constant. Now you have also u mu, which is the norm of the forward velocity given by c square. Okay, when mu is constant, you can write this from this. So this is c square, u0 square minus u1 square. The solution of this is the equation of hyperbola. Okay, this is the equation of hyperbola, and the parametric equation of the hyperbola is this, where zeta is some parameter. It is known as the rapidity parameter. And then you can work out a naught, which is d u naught d tau. You just work out you just derive this and work out. And then after doing this, you simply have a naught square minus a1 square is given by this. And this is equal to -1. So mu is minus c square d zeta d tau whole square, and which is negative definite, and hence the proof. Okay, so you can prove it simply in this fashion without referring anything, without even referring to the result that we have got mu equal to constant. We are not referring to that. We are just starting from here, writing u0 and u1 in the parametric form in terms of some parameter zeta, because this is the equation of hyperbola. The solution I can always write in this form. And then deriving with respect to the proper time, I get the corresponding components of the proper of the forward acceleration. And then I work out the norm of the forward acceleration, a naught square minus a1 square, in this way. And using the relationship that sine hyperbolic square minus cos hyperbolic square is -1, I get this. This thing is positive definite. This thing is positive definite. You have a minus sign, so the full thing is negative definite. So mu is spacelike. This we have proved as a byproduct. Now, you also have mu equal to constant. So this means that d zeta d tau is constant. Okay, we call this constant as some kappa. We denote this constant by kappa. So d zeta d tau is kappa. So zeta is kappa times tau plus some other integration constant. This integration constant you can put to 0 without loss of generality. In fact, you can always shift your proper time. You can redefine the proper time and absorb the kappa in it. So effectively, you can always make the kappa bar equal to 0. This integration constant equal to 0. It's just redefining the time, proper time, so that the integration constant is 0. You try that at home. Okay. So you define a time nu tau. Tau nu is tau plus kappa bar over kappa. Okay. And then put that thing here and solve for mu equal to constant. You'll end up with tau nu equal to kappa times, you'll end up zeta as kappa times tau nu. So you can set kappa bar equal to 0 without loss of generality. So ultimately, you can always have this whence I have u naught is what? U naught is cos hyperbolic zeta, u1 is sine hyperbolic zeta. So zeta is kappa tau. So I have put it here and put that here. But u naught is also dx naught d tau. U1 is dx1 d tau. Okay, where x naught is c times time. Integrating, I just integrate them and get this, where k0 and k1 are integration constants. After integrating, I have x naught and x1 with integration constant k0 and k1. At the initial point, that is when t equal to 0 and x equal to 0, we demand that the proper time is also 0. Okay. When time is 0, then the proper time is also 0. And putting this in here, we can rid of k0 and k1. So just put the at tau equal to 0 or t equal to 0. The left hand side is 0, so k0 is 0. And here the left hand side is at x equal to 0, the left hand side is 1. This thing is 1, so this is c over kappa plus k1. So k1 is minus c over kappa. And putting these two back in these equations, I have this. And this can be rearranged because x naught is c times t. So rearranging and writing, I finally land up to this equation. This is the equation of a hyperbola with some parameter kappa in it. That kappa could be determined in terms of the electric field, magnetic field vectors, these are constants, and q and m, which are the parameters of the model, of the given problem. But this we have done in 1 plus 1 dimension. In 1 plus 3 dimensions, there is no motion along y and z. So this would be hyperbola projected to 3 dimensions. It would be a hyperboloid. So this is the equation of the world line, that is the path of the particle in the 4-dimensional space-time. So often it's not possible to draw 4-dimensional pictures in a paper. So what we do normally is take one space and one time. It's 1 plus 1 dimension. The other 2 dimensions are suppressed. So this is the first problem. The second problem is that let the electric and magnetic field vectors be given in a reference frame as E equal to x plus 3y, B equal to root 3x minus 2z. Determine the magnitudes of the transformed fields E and B in another reference frame S prime in which they make an angle 30 degrees between them. To do that, we use the relationships. this is one invariant relationship that we know. This is actually F star F, which is E dot B, modulo some factor 4. So one relationship is E dot B equal to E prime dot B prime. So this is one relationship. Now work out E dot B from the given expressions. So E dot B is simply √3. And E prime and B prime must make an angle 30 degree. That is also given. So putting 30 degree, you have you can work out the relation between B prime and E prime. Then you have another invariance, which is this. So there are two invariants, remember. One is F star F, and another one is FF, F mu nu F mu. Okay. So this invariant gives you this relation. And once again, E and B are supplied. You can work out their norms, and the norms will give you the difference of the norms will give you 3. So you can solve. B prime is 2 over E prime. So putting it here on the left hand side, I have this equation. Solving, I get E prime square equal to this. It should be positive definite. So therefore, the minus sign of the square root is rejected. Okay. Otherwise, because then E prime square will be negative. So that root is rejected. You only have to take the plus root. Then it becomes 4, and E prime is the magnitude. Okay, it's by definition positive. So E prime is 2. And B prime is 2 over E prime. This is 1. That is the answer. So we have determined E prime and B prime. These types of problems often come even in the university preliminary exams. And also, I have seen this in some of the universities' entrance exams. And these types of problems are also common in the NET examination. Because it's not a big problem, it's a 2-3 mark problem. You have to just use the invariants to work this out. The third problem is involved. The third problem is the determine the trajectory of a particle of charge q and mass m when subjected to the following: a uniform magnetic field P and no electric field. So a particle of mass m and charge q is placed in a constant magnetic field, and there is no application of electric field. And the second one is a constant electric field and no magnetic field. What would be the trajectories of the particles? These are very common in collimator type of things, where the transverse momentum gives you the amount of energy which actually gives you the gain in the apparatus. The effects are purely relativistic. So first, let's start with the Lorentz force equation. This is the covariant Lorentz equation, Lorentz force, and this is by definition the rate of change of the 4 momentum. The 4 momentum is m times u alpha, and which is components E over C and P. E is gamma mc square and P is gamma mv. And F alpha beta has components. F0i is minus EI, and Fij is epsilon ijk pk. So then F0 you can work out from this F0 beta u beta. So you put alpha equal to 0. So that is the first thing you have to do. F0, first thing is put alpha equal to 0 here. So F0 is dp0 d tau. Then this alpha is 0, and there is a sum over beta. But you cannot take beta equal to 0. So beta should be a space index. So you have this. And ultimately F0 will give you this using the component. Okay. And P0 is E over C. So putting this here, what you ultimately land up to is this relation. So this is one equation of motion. The other equation of motion is when you put alpha as a space index. Here alpha is time, and here alpha is space. Alpha is the index. There are 4 equations for 4 values of alpha. One is alpha equal to 0. The other equations are alpha as space indices. So 1, 2, 3. So I put a Latin symbol here. So then the right hand side, you have fi beta u beta. Now you can have fi0 u0, fi another space uj. Okay. And putting all these things, what you will get ultimately, because your 3-dimensional 3 component of the 4 momentum is the relativistic 3 momentum. Relativistic 3 momentum is gamma mv, not mv. Mv is the non-relativistic 3 momentum. Gamma mv is the relativistic 3 momentum. And dd tau is gamma times ddt. So doing all these things, you get this equation. This is nothing but the Lorentz force equation. P dot is F, the Lorentz force. Lorentz force is Q times E plus Q V by C beta, V by C cross B. Beta is V by C. Now, consider the first case, which is only magnetic field, no electric field. And let's say this magnetic field is constant. And for simplicity, we choose its direction to be the z direction. You can choose any direction you like. For simplicity, I'm choosing it to be the z direction. You can choose the x direction, y direction. You can choose it to be in the xy plane. It's your choice. But to do the thing for mathematical purposes, we take it to be the z direction. Now we have the first equation, E equal to 0. That means this energy, time derivative of the energy is 0. So we have this. And energy is what? Is gamma mc square. Mc square is constant. So gamma dot, E dot is 0 means gamma dot is 0. So I put gamma dot equal to 0. Which means gamma is constant. Gamma is constant means V is constant. Gamma is constant means V is constant. So I have one relationship, which is V is constant. Because gamma, gamma is what? Gamma is 1 over 1 minus V squared over C squared. So when gamma is constant, V is constant. The second equation, which is right here, P dot, E is 0. So P dot is Q beta cross B. So P dot is Q times beta cross B. Okay. And P is gamma M V. So P dot means M times gamma V gamma is a function of V, gamma V dot, but gamma is constant as we have shown above. Gamma is constant, gamma dot is 0. So gamma, it is not gamma V whole dot, that is the time derivative of gamma V. Gamma is constant, so it is m gamma V dot. Now you can say V is constant. V is constant doesn't mean that the vector V is constant. Its magnitude is constant, its direction is changing. So the vector V is changing. Okay. So you cannot put vector V constant. What we have proved is the magnitude of V to be constant, not the direction. Direction is not fixed. So I have another equation, which is this equation. From here, I can write V dot as V cross omega B, where omega B is this thing. This is straightforward. This is known as the gyration frequency. Why is it called a frequency? I'll come to that shortly. And this is nothing but 1 over gamma times omega L. Omega L is the classical Larmor frequency, from which the Bohr magneton, if you remember modern physics, the quantum theory, then the Bohr magneton definition comes from here. That is the classical Larmor frequency. Although here we are not considering any acceleration as such, any frame acceleration. But V dot non-zero means the system is accelerating, the particle is accelerating. So when a charged particle accelerates, it radiates. Larmor frequency is the radiation frequency. This is for the classical electromagnetic radiation. The frequency is known as Larmor frequency. When you do a relativistic generalization, the correction term that comes, the correction factor that comes is gamma. So the Larmor frequency is corrected by this factor gamma inverse, giving you what is known as the gyration frequency. Why is it called a frequency? Well, I'll come to that. Now, you can always split any vector in its longitudinal and transverse components. Longitudinal means it's along the gyration frequency, WB vector, and transverse means it's transverse to the gyration frequency. And remember, this WB is along Z. So this means that V parallel is the component which is parallel to Z, and V perpendicular is the component which is transverse to Z, because our magnetic field is in the Z direction. So I can write V parallel as Vz times Z, or Vz equal to V parallel, whereas V perpendicular is in the XY plane. So I have three components of V: Vx, Vy, Vz. Vz is the V parallel component, and V transverse should be in the XY plane, so that means V transverse squared is Vx squared plus Vy squared. Moreover, you have V parallel by definition. This is the parallel component. So V parallel cross omega B is 0. Okay, V parallel cross omega B is 0, and we also have this very important relation. That is, V dot is V cross omega B. So V parallel dot is V parallel cross omega B, and V transverse dot is V transverse cross omega p. V parallel dot is V parallel cross omega b, and which is 0. So that means V parallel dot is 0, or V parallel, the vector V parallel is constant. V parallel is along Z, which we have just shown here. So this means this thing is constant, and V transverse squared, as I have written, is Vx squared plus Vy squared. Okay, and this is constant as well. Because V squared is constant. So what I had proved before, I had V equal to constant. That means V squared equal to constant. V squared is what? V parallel squared plus V transverse squared. V parallel is constant, so that means V transverse is constant. So V transverse is constant. Now, this is one equation. V cross omega b is V dot. The parallel component is V parallel cross omega b is V parallel dot. And this is 0. So V parallel dot is 0. The other thing is V transverse dot equal to V transverse cross omega b. Now V transverse is in the xy plane. So I can have, this is the cross product. So what would be the x component? Vx dot would be Vy omega b, and Vy dot would be minus Vx omega b. You just take the, because you take the x component and the y component of this equation. You get this because of the cross product. So that Vx dot square plus Vy dot square is V transverse squared omega b squared constant. Okay. Now from here, you take the second derivative, Vx double dot, which is, this is constant. So this is Vy dot omega b, and Vy dot is minus Vx omega b. So this is minus Vx omega b squared. So what we ultimately get is Vx double dot plus omega b squared Vx equal to 0. So this is a simple harmonic equation. Omega b acts like a frequency, and hence it is known as the gyration frequency. The particle gyrates, and this is the gyration frequency. Particle gyrates under the influence of the constant magnetic field. You have to solve this, you have to write the general solution, but you have to keep in mind that you also have the first order equations. These are the first order equations. So merely solving the second order equations will not do. The solution must satisfy the first order equations as well. Okay, and the first order equation gives you this. So you have to have a solution satisfying this thing. And the solution, you can check for yourself. The solution can be written in this fashion. These are, of course, sinusoidal solutions with delta as the phase. And in addition, you have Vz. Vz is V parallel equal to constant. And this is in the along the Z direction. So you have all sorts of things, Vx, Vy, and Vz. Vx is x dot dx dt, Vy is y dot, and Vz is z dot. All of them are constants. So solving further, you get x, y, and z. with integration constants. These are integration constants, x naught, y naught, and z naught. This is a sinusoidal, so very easy to integrate. So after integrating cos will become sine. Here the sine will become cos. And here it's constant. So after integrating, you have constant times time. So that's what you get. And in the vector notation, combining these three, the components, you can write in the vector form. So what you see here is that this is very interesting. This is a sort of a circle, right? This is a circle, but there is this is the radius of the circle. This is the circular projection on the xy plane. So this is, you can say, the amplitude of the circular projection of the path on the xy plane. Okay, this part. But this circle moves with time, and as it moves, it squeezes. And the trajectory x is a circular helix with pitch angle v parallel and radius a. So it's a helical path. It's a circle, but the circle spirals like this as we go on. So it's a helix. It's a circular helix. Circular helix means it is a circle which goes on like this. Circle moves. Okay, and every cross section is a circle because the cross section you get is a circle. So the trajectory is a helix, helical path. The xy plane projection is a circle, and the full trajectory is helix. Now, for positive charges, if the charge is positive, the projected circular motion in the xy plane is clockwise. If B points to the observer, and anticlockwise if the observer looks in the direction of B. That you can check for yourself by checking the cross product we had before. So the sign is very important. So I urge you to check at home that this is indeed so. So this gives you the first part A of the problem. Part B. Can I take 10 minutes extra because I want to finish this?
Sure, sir. Yeah, please, sir.
Okay, because there's no more class left, so I'll finish it in 10 minutes.
Yeah, surely, sir.
So the next case is B equal to 0 and E equal to constant along the x direction. Okay, E equal to constant. So now the particle is placed in a constant electric field. The magnetic field is 0. And we choose the electric field to be along the x direction for simplicity. We can choose any direction we like. We choose the x direction to be the direction of the constant electric field. And we also choose the initial velocity, the direction of the initial velocity is along y. Okay, the initial velocity of the particle, that is the particle's velocity at time t equal to 0, is along the y direction. You can once again choose any other direction you like, but here I have made this choice. Okay, you can choose the z direction, you can choose some other direction. It's your choice. No problem with that. The ultimate results will not be hampered by this thing. Now you have two equations. One is the energy equation, that is here B is 0. So you have only the electric field, and the electric field is along the z direction. The first equation you had is uh, um, the first equation is the energy dot E dot equation. So this is E dot equation. E dot is Q E dot, and the second equation is the P dot equation, which is the Lorentz force, that is QE plus beta cross B. Now B is 0, so this goes. So you have just P dot equal to QE, and E is along the x direction, and P is gamma mv. So this is gamma mv dot. Now, so you have this equation. This is the second equation, the z component. First, take the z component of this equation. So there, this is a vector equation. So there are actually three equations. So the z component equation is gamma m vz dot equal to 0, because this is in the x direction. So nothing in the z direction. So the right hand side is 0. That means gamma m vz is constant. Gamma m vz constant means it has the same value it had at initially. And initially the value is 0, because we have chosen the initial velocity to be in the y direction. So nothing in the z direction. So this is 0. So this means gamma vz is 0. Gamma vz is 0, but gamma in general is not 0, because gamma contains v square, and v square is vx square plus vy square plus vz square. So that is in general not 0. What is 0 is, then we can conclude that vz is 0. So the first thing we note that the entire motion would be in the xy plane. So we'll not make any allusion to the z. The vz is 0. Okay. Now the y component. The y component similarly will have a right hand side equal to 0. So this is constant. So that means it has the same value it had in the at the initial time, and initial time the value was v naught by our stipulation. V at initially is v naught along y. We are taking the y component. Okay. So vy is gamma naught v naught over gamma, where gamma naught is the initial value of gamma. That is 1 minus v square by c square at t equal to t0, to the power minus half at t equal to t0. At t equal to 0, at t equal to 0, v is v naught. So gamma naught is this. Now the x component. X component, electric field is in the x direction. So in this case, for the x component, the right hand side is not 0. You have to solve this equation subject to the condition that Vx is equal to 0 at t equal to 0. We have stipulated V to be along y initially. So V is only V0 times y. So nothing along x. So Vx is 0 initial. If we do this, then we have this relation. Okay. And this is this I can write in this fashion, where k is I'm denoting this quantity q over m as this constant k. Now this is the so we have exhausted the one of the equations, that is the p dot equation. Now the E dot equation. E dot is E dot is E dot is Q E dot V. Okay. So it is Q E dot V. E is along x direction. So this is Q E Vx. And E dot is gamma dot mc square. So from here I can find the equation for gamma dot. Okay. And Vx we have just worked out here. So putting that, I finally land up to this equation. This is, you can see, this is gamma square dot. The solution subject to gamma is initially gamma naught. So subject to that condition, the solution is this. Now, very interesting situation. This is fine. What we get from here is that as t becomes larger, the starting time is t equal to 0. As we go on, as time elapses, gamma approaches infinity. And gamma is what? Gamma is gamma squared. Gamma approaches infinity means gamma squared approaches infinity. And gamma square is 1 over 1 minus v squared by c squared. So that means gamma square is 1 over 1 minus v squared over c squared. So gamma approaching infinity implies v approaching c, or v squared approaching c squared. Then this will be 0 and something divided by 0, which is undefined or very, very large, you can say. So v square approaches c square, and the whole entire motion takes place in the xy plane. We have just shown that the vz is 0. So this is vx square plus vy square. At large times, that would approach c square. What does that mean? This means that vy is v naught gamma naught over gamma that we have worked out before. Vy is v naught gamma naught over gamma. So when gamma goes to infinity, vy goes to 0. Now this is very interesting. You see, Newton's first law of motion in classical mechanics is violated in the original sense. So here comes relativity. You see, despite the fact that there is no field in the y direction, we have our electric field along the x direction. E is along x direction. So nothing applied in the y direction. Yet the speed in the y direction decreases to 0 after a sufficiently long time. This should not happen because this is then something which is not customary to an inertial coordinate system. But the thing is still inertial. It is because of the purely relativistic effect. There's nothing wrong with the inertial system. It's the law of inertia which needs to be revoked. The law of inertia is the Newton's law, Newton's first law of motion. That needs to be revoked. Why? Yes, the reason is purely relativistic. As gamma increases with time, so does the relativistic mass gamma m and the total speed v. Therefore, to conserve momentum, the transverse speed along y must decrease. So although you have not given field along y, your Vx, your total speed is increasing. Okay, and your Vx is also increasing. That is, the in the direction you have applied the field, the particle starts to accelerate. Particle accelerates in that direction. If it accelerates in that direction, in the transverse direction, it must decelerate. Although no field has been applied to the transverse direction, yet the particle decelerates in the transverse direction, so as to maintain its acceleration in the forward direction. Now, the rest of the things are straightforward. You have worked out Vy equal to y dot and Vx equal to x dot. So solving this, you can solve them. Okay, the form of gamma also worked out. So solving them, this is the parametric solution which one gets, and this is the parametric equation. These are the parametric equations of a catenary. Catenary, you have often seen. I mean, often these police cordons are catenarized. You can see something like this. So they put up chains between rods. So the chains are hanging like this. So this is a sort of a catenary. Unfortunately, I don't have time to go through the fourth problem. This is very interesting problem. This is on the transformation of the fields. So you have to transform the frames. The condition that is required is to transform in such a way that in one frame the magnetic field vanishes. Okay, and in one frame the electric field vanishes. So you have to transform to a frame in which the magnetic field vanishes or the electric field vanishes. So the conditions are for those are c square less than half and c square greater than half, where c is the constant that is given. So these are the conditions. Please look into this, but then I don't have time to explain all these things. I will post this thing. So if you have any queries, you can contact me over email. My email is supplied to you. You can write email. If there is a stringent need, I'll supply my WhatsApp number. You can also chat with me over WhatsApp or any other thing. Okay. So with this, I'll end here. I hope the things are quite exhaustive, although there are a plethora of issues which I could not touch on. Anyway, I guess people got help from these lectures, at least some bit of help. The fourth question I cannot do. I'll post this thing. I'll post this thing. You can go through the fourth question. If you want further clarification, you can drop email to me. My email is given in the lecture notes which I have shared with you. Okay, so you can drop email explaining what are your doubts, but please try yourself. The solution of the fourth question is all given here. Okay. Yeah, with this I'll end.
So thank you, Dr. Sur. I think you did much more than I thought that you would be able to do in these 5 days of your lectures. But wonderfully, you have given a complete guidance. And once, if anybody would sit through your lectures on YouTube again, along with a book and a pen and a paper, scribbling down and trying everything on their own, I'm sure it will be very helpful to you. And in case it's not, for some query or the other, a small one, you could always attend on email, and it would be better for them this way. So thank you so much. And today it's really a great day. We have come to the end of our 11-week course, and tomorrow is our valedictory function. And
Yeah, you have two public lectures tomorrow, right?
yes, it'll be Professor Ghatak giving at 5 o'clock, and Professor Anurag Professor Anurag Sharma will give at 5 o'clock. He will speak about ubiquitous photonics, and Professor Ghatak will speak about the famous equations of Einstein and the physics related to that. And you are kindly invited. The invitation also comes to you through email. However, I am requesting you personally to at least log in for some time. Then definitely for the valedictory, which will start at 7 p.m. If you cannot spare time earlier, but we would be happy to have you from 5 p.m. itself. So it's a great day for us, and it's a great day for all those who are present here to be, continuously learning every evening. And I'm sure this is an example of the only kind in the whole country in this time of pandemics. And you are nicely ending up the whole series in a very nice note and with a very nice feeling. And for that, I'm grateful to you. Thank you so much.
Yeah, you are most welcome.
So students, please fill in the feedback link, which is there on your chat box. And with that, we shall end the session today. And we all, in my thanks are included your thanks also to Dr. Sur, who has done wonderfully well in explaining all these things. And we will be happy to have any links to your recordings if you are teaching your own students. Those recordings, if you put them up in a public platform, or anywhere or in the departments, then these students can have the link and they can benefit further. So that would be very nice. So with those words, Dr. Neetu, if students kindly copy the feedback link on your web browser so that we can end the meeting. And I wish that each and every one of you is present tomorrow evening for the talks. Dr. Neetu, do you have the last slide with you for tomorrow?
Yeah, just a minute, ma'am, sharing.
Yeah, no problem, no problem. Can I share something meanwhile?
Yeah, sure, ma'am.
Yeah, please. So here it is. I think it's visible now. Is it? Is my screen visible with this?
Yes.
Yes, ma'am.
Yeah, so that's students. This is the poster for the valedictory function.
Yes.
It will come on your WhatsApp groups also now, where you can read you can read the details. It will start at 5 with Professor Anurag Sharma, 6 with Professor Ghatak, who will be also present right from 5 o'clock onwards. And then at 7 p.m. we'll have valedictory function. So you all are invited and you must be present on the last day of this very nice series. So I think that would be enough, Dr. Tiranjita and Dr. Neetu. So you can now stop the live recording and also end the session.